So we're going to start off today with some introductions of the teaching team. That's me, Anand. I'm a fourth-year PhD student in computer science. I work with Professor Andrew Ng on machine learning and applying machine learning to different problems, mostly in healthcare. We also have a wonderful team of teaching assistants. You will meet the rest of them through the quarter in office hours and such. Okay, so the goals of this course. What are the goals in this course? So by the end of the course, we want you to be an expert in machine learning, which means you understand the internals of how machine learning algorithms work, not just using them, but understanding what's happening inside the algorithms. That's the main, I would say, goal number one of this course. Goal number two is to enable you to build machine learning applications, which means having a good understanding of what algorithms to use and which scenarios. How do you decide whether a given problem is a good machine learning problem? Not all problems are good machine learning problems. And once you know that a problem is a good machine learning problem, how do you treat it as a supervised learning problem, unsupervised learning problem? We'll go through all those things, right? And the third goal is also enable you to be able to start doing machine learning research, which means making you familiar with a lot of the terms and concepts that you will encounter if you pick up and read a machine learning research paper. So those are the top three goals for this course. Prerequisites. So machine learning is part mathematical and part computer sciencey, in the sense it's really the culmination of both computer science and statistics. So you will need to have basic computer science principles. You'll need to know them. For example, you need to know what is big O notation, right? You need to kind of understand what's computation versus what's memory. Basic computer science principles. You'll need to be comfortable writing non-trivial programs with Python and NumPy. It would be great if you're comfortable with recursion. Some of the ideas from recursion will be useful when you're translating algorithms to kernel methods. We'll go into detail about them later. So, we will assume that all of you are comfortable writing programs, especially in Python, or at least be willing to put in the time and effort to pick it up. The other big prerequisite is probability. You should have taken some kind of a probability course in your academic history so far. So concepts like random variables, distributions should be you should be pretty comfortable with them. You should know what's the difference between a random variable and a distribution. They're distinct things, and you should know already what they are. Things like expectations. We'll be using all these concepts very liberally throughout the quarter. The last prerequisite is linear algebra and multivariate calculus. So you should already be comfortable with things like gradients and Hessians. You shouldn't be seeing them for the first time. You should be comfortable with these concepts already. And things like eigenvalue, eigenvector as well. So a word about the honor code. So you are strongly encouraged to form study groups. In fact, I would say forming study groups is a key step for being successful in this course, especially if you're not so comfortable with the prerequisites. Please do form study groups and work together in study groups. However, you should still write up your homeworks and write up your code independently, right? So it is fine to discuss and work on solutions together. And once you're done with your study group meeting, put aside all the material that you used during the study group and independently from scratch, write up your homeworks by yourselves in your own words. Please do not refer to the material that you used in your study group session while writing up your homeworks, right? Another important note is that it is in violation of the honor code to refer to homeworks and solutions from previous years, whether they are the official solutions released by this course or solutions written by some other students in a GitHub or wherever. So it is against the honor code to refer to solutions from the past. And we are very serious about the honor code, and though we will, we will not actively look for honor code violations, we trust that you will be you'll be following them. So the course structure, there are 3 homeworks. Each homework will be about 2 weeks long, and each homework will count towards about 20% of your final grade. And there will be a final exam. It will be a take-home final exam. The reason it's a take-home is because you need a computer to do your final exam. There will be some code, more details on that towards the end of the quarter. But it's going to be a take-home final exam, very likely a 24-hour take-home final exam. We haven't yet decided what's the exact start of that, when the exam will start, but it's going to be a final exam during the final slots. Logistics. So the course website is on. It's up. It is cs229.stanford.edu. On the course website, we have the office hours calendars, the course calendars. There are 2 calendars up there. One is for all the office hours, when each TA is holding their office hours and where exactly. And the deadlines are part of the course calendar. So we can have a quick look at the course website. Anyways, it's not opening over here. Anyway, so the you can look up the course website. On the course website, there are 3 big buttons. As soon as you open them, one button is called Syllabus. Let me see if I can. There you go. Okay. So you have 3 big buttons: the Syllabus, link to Piazza, and the calendars. So on the calendars, there are 2 calendars. First one is the office hours. You can click on this and add it into your Google Calendar if you wish to do so. But the exact office hours of every TA is out there. And if you scroll further down, you'll see the course calendar. Basically, we are in this lecture right now, and you'll find details about when each p-set is out, when each p-set is due. All the deadlines are in the course calendar. So if you want, you could just add this to your personal calendar to keep track of the deadlines. And then we have the syllabus page. So on the syllabus page, we have a collection of topics that we're probably not going to cover all of these, but we are going to cover a pretty big subset of these topics. And further down, here is going to be a lecture by lecture of what we are going to cover in each lecture, with the corresponding slides or notes corresponding to that lecture. Yeah. And the syllabus page, this will be updated through the quarter depending on what the actual progress we make is. Right? And Piazza forum. So all of you should have received an invite to Piazza already. If not, click on the Piazza link and enroll right away. Piazza is probably the most important platform for the course in terms of logistics, because all announcements will be made on Piazza. The homeworks will be released on Piazza, and anything that you need to know in terms of the final exam logistics, all those details will be announced on Piazza. So please sign up on Piazza and monitor it. Gradescope, all the submissions will be done on Gradescope. If you haven't used Gradescope before, spend a few minutes to get familiar with it. The homeworks will be uploaded by you into Gradescope directly, and we will grade them on Gradescope. Again, for Gradescope also, you should have received invites by now. If you have not received your Gradescope invite, create a private Piazza post. So in terms of any questions that you have through the quarter, your first destination will be Piazza. If it is a question related to the course content, about the course logistics, create a question on Piazza. It's very likely some others may have already created a similar question, so you can either, if you know the answer, help them out, or if you don't find the question, post it there. If it is a question that is specific to you, in the sense, for example, if you're not able to submit a homework on time and you know that up front and you want an extension, things that are specific to you, or if you have an OAE letter, create a private Piazza post. Things that you don't want the rest of the class to hear about. If there are things that you want to, if there are things even beyond that you want to, say for example, just let me know, and not even let the TS know, just send me an email directly with the word CS229 in the subject. So that's about the logistics. Any questions on the logistics? I'll take that as a no. Okay, moving on. All right, so what is machine learning? So the term machine learning was coined by Arthur Samuel in 1959. And one of the very early programs that kind of got people interested in machine learning was a checkers playing program written by Arthur Samuel. So it was a program, probably most of you know what checkers is. It's a two-person game. There is a checkers board that looks like a chessboard, and you have white and black pawns. It has certain rules. So Arthur Samuel wrote a program in a few years before 1959, and it became popular in 1959, where the program would learn to play against itself without any kind of strategy being explicitly programmed into it. Right? It learned to play against itself, and it improved its game playing performance as it experienced more and more games against itself. And eventually, it learned to play checkers better than Arthur Samuel himself. I don't know how good a player he was to begin with, but it got pretty good by just self-play. There was no strategy coded in by Arthur Samuel into the program. Only through experiences, the program learned to play better. And that was kind of the event that kind of sparked widespread interest in machine learning. A more common definition by Tom Mitchell, he's a professor at CMU, is machine learning is the study of computer algorithms that improve automatically through experience. Now, experience is a loose term. What do we mean by experience? Most of the times by experience we mean prior data, right? Examples from the past, where the machine learning algorithm itself is a very generic template algorithm. You don't, and you feed the algorithm data from the past, what you call as training data, and the algorithm analyzes the data that's given to it, and looking for patterns in the data, the algorithm improves its performance at whatever task it is designed to operate on. So the key here is data or experience from the past that distinguishes machine learning from other fields. Right? Machine learning is also related to the field of artificial intelligence. So AI is a much broader term, and we see the terms AI and machine learning being conflated a lot of times, especially in the news and media. But strictly, if you look at the definitions of AI and the definition of machine learning is a subset of AI. Right? AI is a much broader field. AI is about building programs where the programs operate at the level of performance of say a human being, for example. Again, that's a very loose definition of AI, right? So AI is is a broader definition, and it deals with algorithms that perform at a cognitive level similar to a human being. Machine learning is one approach of how to implement such programs. For example, you could implement an AI program that does not look at any kind of training data. You just use your smarts and write up a very smart program that works really well and behaves as at the level of a human in terms of performance, and that's still AI. But that's not machine learning. In machine learning, data is the key. You look at past data, use it as a training set, or you build a simulator from which your program can kind of build experience by interacting with its environment. And that program, which is looking at data or which is which is getting experience in some kind of a simulator, improves its performance over time. That's machine learning. That's one way to make your programs intelligent. Right? However, most of the recent attention in artificial intelligence is due to machine learning. Right? Artificial intelligence has been around for a while. Machine learning has been around for a while. But some of the recent advances in machine learning has made machine learning very successful. And therefore, the interest in artificial intelligence is kind of reinvigorated again. And even within machine learning, there is a specific type of machine learning called deep learning, which has actually seen the most advances recently. So it's good to have this clear picture of AI, which is a much broader field, which is dealing with programs that operate at a similar cognitive level as a human being. Right? AI does not tell you how to implement such programs. Within AI, machine learning is a subfield which prescribes one way to implement such programs. That's basically look at prior examples and learn from examples. And even within machine learning, there is a subfield of machine learning called deep learning, which uses something called neural networks, which we will see later in the course. And that's the field that has made a lot of progress in the last 5 to 10 years. Okay? So here are some examples of where machine learning has made a lot of progress. So computer vision and image recognition. This is a field that has probably undergone the most progress in the recent years. There is a famous data set called ImageNet, a computer vision data set, and there is a kind of model called a convolution neural network, which together, more or less revolutionized computer vision. And this is all recent, since after 2012 and 2015, within the last decade. And it has also significantly improved autonomous driving, where machine learning techniques are used to sense where pedestrians are, where the stop sign is, where the traffic lights are, and it's a key component for autonomous driving. Machine learning has also significantly improved speech recognition, and things like it has made possible things like voice assistants, like Apple Siri or the Google Assistant, etc. Language translation. So Google Translate now uses machine learning, or from what we know, from what Google tells us, it uses deep learning. And in fact, there was also a paper from Facebook, I think last year, which does unsupervised translation, which means just give it a corpus of a whole bunch of English sentences and English documents, and just give it a whole bunch of, for example, French documents, and just by looking at them, where the algorithm was never told what is a matching English and French statement, but just looking at two different corpuses, it learned to translate sentences from one language to another. And similarly with Google Translate, they had this paper a few years ago where they built a single model that could translate from various pairs of languages, and that model automatically learned how to translate from new pairs for which it had never seen a training example before. And those are examples in language translation, very exciting field. There's also a lot of progress happening in reinforcement learning or deep reinforcement learning. And most of the progress there has been in game playing. Like, for example, DeepMind over the last few years, they built reinforcement learning models that could play Atari games at the level of humans. So you feed the model the pixels from the display of an Atari game, and just by looking at the pixels of how the game looks, the agent will controls different actions, and the agent learned to play Atari games at a superhuman level across a whole, across 30, 40 games. And also AlphaGo. Until very recently, Go is another board game, and it was widely considered to be extremely difficult to play because you need a lot of strategy, a lot of planning. And after chess was kind of conquered by computer programs in the 80s and around the 1980s, Go was then thought of as the next big board game that's really hard to kind of beat. And AlphaGo again was built by Google again, which plays better than like the world's top Go players. Those are some of the recent progresses, and some preview into the course, what we'll be doing through this quarter. So we're going to look at different supervised learning algorithms, unsupervised, deep learning algorithms, some learning theory, and some reinforcement learning. So most of the time will be spent on supervised and unsupervised, and a good amount on learning theory, and maybe a little bit on reinforcement learning theory. So in supervised learning, we're going to look at problems and classify them as regression problems versus classification problems. What are regression problems? When the output of your machine is some kind of a real valued output. For example, if you're trying to predict the wind speed tomorrow at Stanford, and you're going to build a machine learning model to predict the wind speed based on today's weather conditions as the input, the output is going to be a real valued number, some kilometers per hour or miles per hour. So that's a real valued number. So that's, for example, a regression model. Classification model, for example, if the output is binary or some kind of a class, will it rain tomorrow? Yes or no? Right? That's a classification problem. Given today's conditions, if you want to predict whether it's going to rain tomorrow, the answer is yes or no. And you can classify machine learning algorithms in along many different dimensions, as generative versus discriminative, probabilistic versus non-probabilistic. So any given machine learning algorithm, you can kind of place it on this hypercube of all these dimensions. And kind of taking a step back, what is supervised learning? Supervised learning is a kind of machine learning technique where the training data that you have come in pairs. Each pair has an input and an output, right? An input is what you feed into the machine learning algorithm, and the output is what the machine learning algorithm should output, right? So, and that's called supervision, because for each example, you're telling the algorithm what the right output is. So that's where the supervision comes in. In unsupervised learning algorithms, you give the algorithm some data. There is no explicit supervision, and you just ask it to look for patterns or interesting structure in the data. And the output of your algorithm is that interesting structure or an interesting pattern. And again, we kind of classify unsupervised learning algorithms as those that look for clusters versus those that look for subspaces. It's fine if you don't fully understand these terms now. I'm just giving a flavor of what's to come in the rest of the quarter. And deep learning is what's also commonly called as representation learning, where the deep learning can kind of plug into you can view deep learning in a supervised setting, unsupervised setting, in a reinforcement setting, etc., where you're trying to learn representations of your data. Whereas in non-deep learning approaches, you are manually feeding in what the right representation is for the supervised or unsupervised or reinforcement learning algorithm. Whereas with deep learning, you're letting the algorithm itself learn the representation as well, along with the final task. And then we'll cover learning theory, super important concepts of the bias variance decomposition, bias variance trade-off, generalization, and uniform convergence. Why do we expect a model that was trained on this training set to even perform with any level of accuracy when you start using it in the world, when you put it to production? Because you trained it on this specific training set. Why do you expect this model to work well in the real world? Questions like that, we're going to answer them in learning theory. And that's probably, the learning theory is probably the part of the course that makes this course interesting, in the sense you learn principles that are common across learning algorithms, common across learning algorithms that have not yet been invented, right? The foundational principles of why machine learning works. And then we'll spend some time on reinforcement learning as well, though not a lot. So here's an example of a supervised learning algorithm, image classification. So these are examples of few images of handwritten digits. This comes from a very famous data set called MNIST, where the input is a set of pixels. I think this is 24 by 24 pixels or some resolution like that. And they are black and white images. In fact, they are grayscale images, where you have the pixel value at each location. You feed the set of pixels as input to some learning algorithm, and the output of the learning algorithm is going to be one of digits 1 through 9 or 0 through 9. It has 10. It's a multi-class classification problem. So the output is it's a classification but not binary. It's one among 10 classes, and you want to learn a machine learning model given this training data, which is able to predict what the handwritten digit is for digits it hasn't seen before. In fact, you'll be working on this data set and implementing a neural network to build a handwriting digit classification in one of your homeworks. Okay, so unsupervised. Here's an example of an unsupervised learning. So in this example, it's what's commonly known as the cocktail party problem. So imagine there are n speakers. In this case, assume there are 2 speakers who are in a cocktail party, just the 2 of them. And there are 2 microphones that are placed in the room at some specific locations. Now, the 2 microphones are recording what the 2 speakers are speaking, and each of the recording is some mixture of what the 2 speakers are saying. And the task here is now to take these 2 audio clips. Each of them has a different mixture of the 2 speakers, and the machine learning algorithm is expected to output two different waveforms where the voices are separated. Right? So all that you're feeding into the algorithm is just 2 clips. You're not saying, there's no kind of supervision telling, speaker 1's voice sounds like this or speaker 2's voice sounds like this. There's no supervision whatsoever. You're just feeding it 2 clips where the clips have mixed audio of 2 different speakers, and the model outputs the separated voices. So let's see if the audio works here.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Right? That's, from one microphone, there were 2 speakers.
1, 2, 3, 4, 5, 6, 7, 8, 9 y 10.
Right? That's from another microphone. Probably the sound of one of the speakers was a little louder than the second one, or vice versa. And when you separate them,
1, 2, 3, 4, 5, 6, 7, 8, 9 y 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
right? So all what you gave the algorithm was these two audio clips and nothing else, right? Just two wave files, and it analyzes the audio waveforms, looking for structures, and it's able to separate the voices with no supervision whatsoever. And you're going to be doing one of this in your homeworks as well. It will not be two, but actually a set of 5 audio clips that are mixed together, and you're given 5 different audio files, and you will implement the ICA algorithm that we're going to cover in the course, and separate the audio into 5 distinct clips. And finally, reinforcement learning. So here's an example of reinforcement learning where the goal of the algorithm is to control what's commonly called the inverted pendulum or the cart pole. So imagine you have a stick and you're trying to balance a stick on your hand, a vertical stick on your hand, and we are trying to control this this cart pole agent in order to keep the stick that's placed on it well balanced, right? So when you start a learning algorithm from scratch, so this is episode, so each trial is an episode. Once the stick falls, you start the next episode. And for example, this is episode 0. It is falling, falling, falling. Now it's episode 1, falling again. Episode 2. Fell down. Episode 3. Fell down. And you train this algorithm, you continue training it for more episodes, and eventually it'll get better. I stopped the algorithm for this, stopped at about 130-ish. But if you let it continue, it's going to learn how to balance the cart pole for potentially indefinitely long. There you go. Oops, I think it falls off the table or something. Anyway, so again, this is going to be on your homework as well. You're going to write a reinforcement learning algorithm that's going to learn in a simulator like this how to balance a stick on top of a cart pole. Yes, question.
Just out of curiosity, for the previous example that you gave, is it required that you have as many clips as you have speakers?
So the question is for those who are watching the lecture online, is it necessary to have as many number of audio clips as the number of speakers? Yes, that's exactly right. You need as many number of audio clips as the number of speakers. Okay, so that's about it for the introduction. So for the rest of today, we will be so for the rest of today we'll be covering doing a review of linear algebra in case it's been a while since you took linear algebra, to brush you up and familiarize you with the concepts that are more important for this course. And in the next class we'll be covering matrix calculus and some probability and statistics, and from onwards we'll be getting into actual machine learning models. Yes, question.
You said that in unsupervised learning we try to find the structures,
Mm-hmm.
and then in a paper you said unsupervised learning translation. So you give it a system and then you ask for mapping. How does that work? Because if you are asking for mapping, you need to go to supervised domain.
Yep. So the question was in unsupervised learning you're just given a data set and asked to find structures in the data. And I also spoke about an example with the language translation where a model was just given unpaired mappings of language and it still learned how to map from each other. The answer to that is a little technical. Let's take that offline. After the lecture, come up and we can talk about that. All right. So I'm going to be assuming all of you are familiar with some basics of linear algebra, in the sense all of you know what a matrix is, know what a vector is, what you can do with vectors and matrices. So we'll be reviewing them, but also I'm going to be assuming some familiarity from all of you. So first of all, some notation. So what's a vector? Right. So for the purposes of this course, we will assume that a given vector, let's call it V, is an element of R to the D. Now, let's make sure all of us understand what this means, right? This means an element of, from set theory. So V is a vector. It is an element of this set, and this set is a d-dimensional real space, right? So what's a d-dimensional real space? So this is, imagine this is the real line, and this is x, y, z. So this is an example. This is R3 because there are 3 dimensions, right? So a vector is an element of a d-dimensional real space. And vectors are, when we say it is an element, it means it is a point that lives in this d-dimensional real space. This vector can also be represented as V1, V2, Vd. We generally write a vector generally is considered as a column vector. We write it as a column in this course. You can also write a row vector as V transpose. It's going to be V1, Vd, right? So what do these numbers mean? These numbers are basically the coordinates of this point. Right? So this is V1, this length, and this length is, maybe I should write it here, V1, V2, V3. Right? And this point over here is V. Right? Similarly, we also have a matrix. Right? So we write matrices as, let's call it a letter A. So generally matrices we use capital letters. For vectors, we use small letters. And we say is member of R m by n. Right? You can interpret a matrix A as an element living in an m by n dimensional real space. What does that actually mean? Right? So you can think of that as so a matrix is a grid of numbers, real valued numbers for the purpose of this course. Through the course, we hardly ever deal with complex numbers. So it's going to be only real numbers. Think of it as a m by n grid of real numbers. And that's a matrix. You can interpret this as n column vectors of m dimension each, right? Or you can think of it as m row vectors of n dimension each. Right? There is a special matrix called the identity matrix, which is ones along the diagonal and zeros everywhere else. I just write a big 0 to indicate that all the individual cells are 0. You can also have a diagonal matrix, where a diagonal matrix is one where all the cells except the diagonal are zeros, and these could be any value. There's something called a symmetric matrix. A symmetric matrix where A equals A transpose. What is transpose? Switching rows and columns, exactly. So a transpose of a matrix, in this case, take the first row, the first column, and treat it as the row of the transpose, right? And take the second row, second column, and make it the second row, and so on. Right? The property that the transpose satisfies is that Aij equals A transpose Ji. Here, I and j are the row and column indices of a given matrix. So when you transpose it, the row number becomes the column number, and the column number becomes the row number. The trace of a matrix is the sum of the diagonal of that matrix. So take a square matrix and sum up the diagonals, and that's the trace. Let's look at some basic operations that you can do with vectors. So if you have two vectors, you can kind of combine them in two different ways, right? So the first is called the inner product. So first this. So vector operations. Given two vectors, what can you do with them? So the first is the inner product. And technically the inner product and dot product are distinct concepts, but in this course they're going to be the same. So the dot product. So one way to think of the inner product is if you have two vectors, x, y, both in Rd. So in order to perform the inner product, the two vectors have to be of the same dimension, for example d, and the inner product is the sum over I equals 1 to d xi yi, right? And this is also written as x transpose y. So this is the mathematical representation of the dot product. You could also think of this as like this. You think of a vector written as a row vector, another vector written as a column vector. The two have to have the same dimension, and when you perform the inner product, you get a scalar. Right? You feed in two vectors, the output is a single number. Right? You've lost the angles or the orientation of the vectors once you perform an inner product. Right? The other operation you can do with two vectors is anybody? You can do the cross product. The cross product, however, is not very interesting for us. You also have something called the outer product, right? So the cross product and outer product are different things, right? So in cross product, you're given two vectors, and you find a new vector that is perpendicular to the plane in which the two vectors are. But here we're going to talk about the outer product. So we have inner product and we have the outer product. So in the outer product, you can have x in, let's call it R d, and y in R p, right? So for the outer product, the two vectors need not have the same dimension, right? But in a product, they had to have the same dimension. And mathematically, we write the outer product as x y transpose, right? It could also you could also have a different outer product, which is y x transpose. In this case, x transpose y and y transpose x for the inner product was the same. So you could switch the order, but for outer products, if you switch the order, you get something which is a little different. The way to think of the outer product, at least pictorially, is something like this. So right? So think of vector 1, vector 2. So we have a column vector and a row vector, right? So in this case, this is d-dimensional and this is p-dimensional. Right? So with the inner product, we took a row vector, a column vector, and converted it into a scalar. Right? But with an outer product, what we do is you take each and every possible pairs of elements from the row vector and the column vector. For example, take the first element from the column vector and say the third element from the row vector, multiply those two elements, right? And that becomes the first row, third column cell of this matrix. So you take two vectors and construct a matrix out of them, right? By pick the ith element from this vector, jth element from this vector, multiply them, and that becomes the ij element of the matrix, right? So this for the outer product, you don't need the vectors to have the same dimension. And a matrix that you construct from one row vector and one column vector is also called a rank 1 matrix. Right? Why is it called rank 1? Because one way to think of it is made of one pair of a row and a column vector. Right? So that makes it what's also called as a rank 1 matrix. Right? You could also, for example, take two rank 1 matrices, add them up. So these together will give you one rank 1 matrix. Add it with another rank 1 matrix. Right? So the the column vectors have to be of the same dimension. The row vectors have to be of the same dimension, but the two need not be the same dimension, right? So if these two have to be d dimension, these two have to be, for example, p dimension. Here you get a rank 1 matrix, you get another rank 1 matrix, you sum them up element wise, and you get another matrix of rank. So you take two rank 1 matrices, you add them up, you get a rank 2 matrix. So you take two rank 1 matrices and you add them up, you get a rank 2 matrix, assuming the vectors are linearly independent. Right? If the vectors are linearly independent, you take two rank 1 matrices, add them up, you get a rank 2 matrix. Now, what happens if let's say we add k of them. 1, 2. What's the rank of this matrix? Rank k. So the rank of this matrix is actually going to be the less than or equal to min of d, p, and k. So the rank of the matrix cannot be bigger than the smaller dimension of the matrix. Right? So by adding rank 1 matrices, adding linearly independent rank 1 matrices, you're increasing the rank of your resulting matrix, but you can only go up as high as the smaller of the two dimensions. Yes, question? Yes, we will. I will define the rank. For now, let's think of a rank as think of this as a sheet of paper. Like think of this as a matrix, and you add more sheets of papers. You're increasing the rank of the matrix. We will precisely define what the rank of a matrix is in a few minutes. Right? And just by looking at a matrix, if you're just given a bunch of numbers of rows and columns, it's pretty much impossible to tell what the rank of that matrix is. Right? It's superficially you cannot just tell by looking at a matrix what its rank is. Right? It's like an inherent property. There are simple cases. If you're given a diagonal matrix where everything is zeros other than diagonal, yes, you can tell the rank. But in general, just by looking at the values of a matrix, you cannot tell what the rank of a matrix is. Okay, so those are vector-vector operations. Let's look at some matrix vector operations. Right. So matrix vector. So we went over vector-vector operations, the inner product and the outer product. For the inner product, you had to have both the vectors of the same dimension, and you would get a scalar. For an outer product, they could be of different dimensions, and you got a rank 1 matrix. Right. Now let's look at matrix vector operations. So for matrix vector operations, first we're going to consider operations where you have a matrix, let's call it A, and a vector, call it X, and this, let's call it M by N, and this is N. So A belongs to R M by N, and X belongs to Rn, right? So this is and so Ax is now of dimension
M plus
1. So how do you think about this operation? So first you can think of the matrix as a set of rows. Right? So each row has n elements, right? And the vector you're multiplying it is a column vector, right? And all you're doing is the inner product, right? Take the first row, get the inner product with the matrix, and you get a scalar, right? Take the second row, do the inner product, you get another scalar. And you're going to get as many number of scalars as the number of rows you have in the matrix, right? So Ax Rm. You can write this as m by 1, but we assume vectors are column vectors. So if I write just in Rm, it just assume it's m by 1 if you want to think of it that way. Another interpretation of matrix vector multiplication is it's the same matrix, except we're going to think of them as columns, right? M by N. This is N, so this is A and this is X. So this has, I'm just going to use different symbols. Let's assume there are 3 elements, and all right, this has 4. So let's assume this has 4 elements, and the n is 4. A is a m by 4 matrix, and you're trying to calculate Ax. The other interpretation here is, let me use some colors. So here we did inner products, right? Here what we're going to do is pick the first element of X, scale the first column of A, right? And then pick the second element of X, scale the second column of A by that number. By scaling, I mean do an element-wise multiplication of this number with all the elements here. Just rescale it. And pick the third element of X, scale the third column, right? And then you just sum them up along this way. So sum up the scaled versions, right? So Ax is again, you're summing up m-dimensional column vectors that are scaled by the corresponding values in the vector, and that's just going to give you, And whether you do the operation this way or this way, you'll always end up with the same right-hand side. Right? So that's matrix vector. And then you have matrix. So again, for matrix, there are kind of two interpretations of how you kind of visualize the product of two matrices. So let's assume you have two matrices m by k times k by n. So it is important that the number of columns of the first one and the number of rows of the second one are the same, right? And in interpretation number one, we'll go with the inner product interpretation. So you have m rows of k dimensions each and n columns of k dimensions each, right? The dimensions are matching of the row and the column, so naturally we want to do the inner product, right? Now take every pair of row and column vector, so that gives you m times n. So any row vector, any column vector, perform the inner product, and that becomes the cell value of the corresponding ith row and jth column, right? So pick the second row and the fourth column, do the inner product, and that is the second row, fourth column of your output matrix. So matrix multiplication is essentially a whole bunch of inner products that you're doing concurrently in parallel. You can also the same operation, m by k, k by n, and in this case think of them as, right? So now we have k column vectors and k row vectors, right? M and n are different, so this is m dimensional and this is n dimensional, but we have k of each of them, right? Now pick them pairwise, not all possible pairs, but pick them pairwise. So first row and first column, first column and first row, do the outer product, you get a rank 1 matrix, right? So you get a rank 1 matrix of, so this is column 1 from the first matrix and row 1 plus pick the second column and second row, column 1 and row, column 2 and row 2, right? And add k of them. So column k and row k. So the columns come from the left matrix and the rows come from the right matrix. And you add them up, you get another matrix, right? And the matrix that you calculate this way or the matrix that you calculate this way are going to be exactly the same. So they're just two different interpretations of the same mathematical operation. Any questions so far? Yeah. Yeah, so the question is, should this be a rank 1 matrix? So when you take a column vector and a row vector and take the outer product, this will be a rank 1 matrix. And this is another separate rank 1 matrix. And this is another rank 1 matrix. And when you add them up, when you add k of them, you get a potentially, a min of, m, n, and k rank matrix. It will, if the rows and columns are linearly independent, it will not be rank 1. You're increasing the rank as long as you're taking linearly independent rows and columns. But you cannot keep adding matrices, rank 1 matrices, and increase your rank forever. You have an upper bound, which is the smaller of the two dimensions of the row or column. All right, so there was another question of what the rank was, and before we get to that, let's see, why do we need to learn linear algebra for machine learning? Why is linear algebra even relevant for machine learning? So some of the situations where we will end up using linear algebra through the rest of the quarter is, first is represent data. So suppose in a supervised learning setting, let's say you want to predict the price of the house, and the inputs that you're given are things like, the number of bathrooms, the number of bedrooms, the area, etc., you would then represent your training data as X, as where each row X it's also called the design matrix, where each row is an example, is a different example, and the columns corresponds to what are also called as features. For example, this could be house 1, house 2, house 3, house 4, etc. And this could be, say, number of bedrooms, area, number of bathrooms, etc. And this is generally called a design matrix. Right? So your design matrix X is most conveniently represented as a matrix. Similarly, your supervision values, the actual house prices of those houses, is most conveniently represented as a vector. Right? So just to represent your data, it is convenient to use concepts from linear algebra like matrices and vectors. Right? And then we're going to do a whole lot of manipulation with these, like multiply this x vector with another parameter vector called theta, and so on and so on. So we're going to be using linear algebra for representing our data and also doing operations on them. Another situations where we will need matrices is going to be in probability to represent what's called covariance matrices. We will cover probability review tomorrow, and we will go over what a covariance matrix is. So, for example, covariance matrices, they're generally written as, they tend to be symmetric. Symmetric means the matrix and its transpose are the same, right? And we're going to use linear algebra for calculus, multivariate calculus. Right? So things like gradients. So gradients, and I'm expecting you know what a gradient is. So gradients tend to be vectors, right? So you would represent vectors as column vectors. Hessians are matrices. Hessians are basically like, think of them as the second derivative in the multivariate setting. Jacobians. Jacobians are derivatives of a vector valued output from a vector valued input. All of those can be so gradients will be vectors, Hessians, matrix, symmetric, Jacobians, again a matrix, and Jacobian will likely not be symmetric, and so forth. And we're also going to use linear algebra very liberally in kernel methods. You're not expected to know what a kernel method is. I'm just listing it here, just so that learning linear algebra has uses in all these various scenarios. Right? And by calculus, I also mean in general optimization. Given a loss function, we need to minimize it, right? And we're going to use gradients and Hessians and so on there. Right? So yeah, so linear algebra is important, and it's very important that you are comfortable manipulating these concepts such as matrices and vectors, and multiplying them, taking inverses, etc. Any questions before we move on to a few more interesting concepts? No questions? So we saw matrix vector multiplication over here, right? So here's let's do a geometrical interpretation of. So linear algebra is one field of mathematics where it's very easy to visualize things, which makes it really fun and also kind of easy once you kind of get the core intuitions, right? So we saw the matrix vector multiplication. So A, let's call a matrix as A. It's in Rm by n, and let's say you have a vector x in Rn, right? Now, when you do a matrix vector multiplication, you get something called Ax, right? And this is in Rm, right? So one way to think of Ax is through these, row interpretation or column interpretation, right? But an even more useful way to think about this is to think of A as some kind of a function. Right? Think of A as a function. It's, we've been looking at the matrix as a set of numbers, right? So stop thinking of it as a set of numbers, but think of it as a function that takes x as input and outputs, that vector. Now, let's assume we have A in R 3 by 3, right? Which means we have it takes as input values from a three-dimensional space, and its output is also a three-dimensional space, right? Now we are thinking of A as a function, right? Which takes as input. So the inputs are vectors, and the outputs are also vectors. Right? So x is a vector, Ax is also a vector. They are in different dimensions, yes, right? So it takes as input an n-dimensional vector and produces an output which is an m-dimensional vector, right? So let's pick some. So assume this is the A which does the multiplication, and so these are, let's call them x-axis, y-axis, z-axis. A is 3 by 3, and let's say so this is a vector in, this is some x. It lives in a three-dimensional space, and it has, a column representation, right? Multiplied by A, right? And let's say it maps it here in the output space. Now let's take another vector, let's call it, this is some other vector, run it through A, it's going to give you a different output, right? So perhaps it comes here. And similarly, we take a third vector, run it through A, it's probably going to come here, right? So the what this picture is representing is you have this function A. Right? We don't think of it as numbers anymore. We think of it as a function for which we take some point in the input space as the input, feed it into the function, and it outputs a new vector in possibly a different dimensional space. In this case, it's 3 and 3 to make the visualization simple. Right? Now, if A is full rank, which means its rank is 3 in this case, right? There is going to be a unique mapping between every point in the input to every point in the output. There's going to be a one-by-one mapping, one-to-one mapping between every point in the input to a corresponding point in the output, right? Now, if A is such a matrix that makes such a one-to-one mapping possible, A is a full rank matrix, right? Now, so this is input space. This is the output space. Right? Now, you could also imagine that there exists some other matrix, call it B, that takes these values as the input, right? Say the red as the input, run it through B, and it outputs the original point over here, right? Now, if A is a full rank matrix, then such a B will exist, which does the reverse mapping, and this B is also called A inverse, right? So A is the function that takes vectors as input and maps them to some output, and as long as it is full rank, there will be another matrix which is the inverse of it, which takes this as the input and corresponds and outputs the original point as the output, right? Now this is in the case of a full rank matrix. Now what happens if A is not full rank? So this was full rank. Now here, if a matrix is not full rank, it's technically called a rank deficient. Right? So again, this is the input space, x-axis, y-axis, z-axis. Similarly, there is output space, x-axis, y-axis, z-axis. Right? And similarly, we have an A over here. A is again in R3 by 3. But let's assume this is a rank 2 matrix, right? And this was a full rank matrix. This was a rank 3 matrix, so it could uniquely map every point to every other point, and you could go back through the inverse. Now, if it is rank deficient, what this means is, if the rank is 2, it means there exists a 2-dimensional subspace in the input space. Right? So there exists a 2-dimensional subspace. What does a subspace mean? So assume this is the ambient space, is 3-dimensional. Assume this room to be the ambient 3-dimensional space. Any 2-dimensional plane, for example, this paper that extends indefinitely along all directions, is a subspace that lives in this 3-dimensional space, right? Now, if the rank of the matrix is 2, and it is a 3 by 3 matrix, then in this 3-dimensional ambient space, there exists a 2-dimensional subspace that is specific to this matrix, and that subspace must pass through the origin, right? And also a corresponding subspace in the output space, which is also 2-dimensional, which is what makes it, a rank 2 matrix. There is a 2-dimensional subspace and a 2-dimensional subspace. Again, this also has to go through the origin, and there exists a 1-to-1 mapping between points on this subspace to points on this subspace. So a point on this subspace may get mapped here, another point over here may get mapped here. Similarly, a third point here may get mapped here. Right? Now, this subspace extends to infinity in all directions, right? In both the input and output space, and A gives you a unique 1-to-1 mapping between elements in these subspaces. But A is a 3 by 3 matrix, right? It's a function. Think of it as a function for which you can feed any input. Just because a subspace exists for which a 1-to-1 mapping exists, doesn't mean, for example, I may take this point that lives outside the subspace, right? This is, think of this as the ambient three-dimensional space. This is a two-dimensional subspace. What about the point over here where the pen resides? It's not living in the subspace. It's outside the subspace, right? Take such a point that that doesn't live in the subspace. You can still feed this point as an input to this function, and it's going to map it somewhere, right? But where will it map it to, right? The way to think about that is any given point in the input, in the input space of a matrix can be decomposed, right? You can decompose X into two parts. One part so let's assume this is X, and X lives outside the subspace. You can decompose this X into two parts, where one part lives in the subspace and is in a way nearest to the given X, and another part which is this residual from that nearest point to the actual point, right? Which means assume the origin is in that corner, and this is a two-dimensional subspace that kind of passes through the origin, and we have a point over here. This point can be decomposed into two parts. This point is represented by a vector that starts at the origin and ends at this point. You can decompose it into two parts, where one part lives strictly in the subspace, and it extends all the way till it is nearest to this point, and a second part which is a point that is perpendicular to the subspace that originates from that nearest point to this point, right? It's like Pythagoras theorem. You have two components which are at right angles, and any vector can be decomposed into a component that lies in the subspace and a component that is strictly perpendicular to the subspace, right? And I'm sorry, what's the question? Yes, you can call it a resolution, but a more commonly used term is decomposition. So you decompose that vector into two parts, right? And these two parts, when I mean decomposition, I don't mean take the vector, and split it into a two-dimensional versus a three-dimensional. What I mean is, you should not be confusing this decomposition as splitting it into one part that lives in the subspace versus another. That's not what we are talking about, right? What we are talking about is, X can be written as, I'm going to use the word projection over here. So the projection of X onto the subspace plus the technical term over here would be the row space plus projection onto the null space. Now, what does that mean? I mean, we saw two terms over there, a row space and a null space. Now, row space is actually the subspace which gets mapped bijectively to the corresponding, the output subspace, right? This subspace in the input space, right, for which the bijection exists, is also called the row space. And it's called the row space because it is made up of precisely those points which can be represented as linear combination of the rows of A. Right? Yes, question. Are all projections orthogonal? I'll come to that in a moment. Yes. The row space is made up of all points that can be represented as linear combinations of the rows of A, and it is precisely that subspace for which a bijection exists between the output space and the input space. So this is called the row space, and this is called the column space. right? It's also called like the range of, it's also called the range, or you can think of it as the columns. And this is precisely the set of all points which can be represented as linear combinations of the columns of A, right? Now, the point over here, which did not exist in the row space, we said can be represented as the sum of two components. We can decompose it as the sum of two components. One component that lies in the row space and is nearest to X, and another component which is, you can call it, what's left, or the residue, right, which is orthogonal to your row space. And the question was, is the projection always perpendicular to the space onto which you're projecting it to? Yes, the answer is yes. So the way you want to think of it is, let's assume this is the subspace. Right? This is a two-dimensional subspace in this ambient three-dimensional space, and you have some point over here, where this a black pen is, and you want to project it onto the space, onto the subspace. Now, the way you do the projection is search all the points that exist in the subspace, calculate the distance from that space, from that point to this point, and choose the point that has the smallest distance. Right? That point is the projection of the point having the smallest distance from this point is the projection of this point onto the subspace. And the line connecting the true point to the projection point is always going to meet at an angle of 90 degrees. It's always going to be perpendicular to the subspace itself. And it's kind of intuitive, right? So in the subspace, the point that is nearest on this plane to this point is going to be the one that is like directly below it, and so that line is always going to be perpendicular. Does that answer your question? Okay. Yes, question.
So what if the subspace doesn't pass through the origin?
Subspaces always pass through the origin. By definition, they pass through the origin, because this is always going to be some linear combination of the row or the columns, and the linear combination can be just zeros, just 0 times column 1 plus 0 times column 2. So the origin is always part of both the input subspace and the output subspace. Yes, question? Yeah, so the question is, what is row space? So row space is precisely the set of all points that can be represented as linear columns of the rows. Right? So column space is the set of all points that can be represented as linear combination of the columns of A, which means the set of all points that you can obtain by multiplying some vector with that matrix, right? And according to this definition, it is some linear combination of the columns of A, and you take the transpose and you get the row space. Yes, question.
Did you say that these subspaces are essentially combinations of columns of A?
Right, so the question is, are the subspaces? Yeah. So the question is, are the points of different colors, are they the rows or columns of the matrix A? Is that the question? So, good question. Thank you for asking that question. So the points that I'm choosing over here, right, have nothing to do with, in the sense, they need not be either a row or a column of A, right? The points that lie on this subspace can be represented as some linear combination of the rows of A, right? What it means is, so if A has 3 rows, there will be 3 points in the subspace which corresponds to the 3 rows of A. It has to lie there, because what I mean by that is, let's assume A has 3 rows. This is A, it has 3 rows, and this is the subspace obtained by linear combinations of these 3 rows, which means one of the combinations could be 1, 0, 0, right? 1 times the first row plus 0 times the second row plus 0 times the third row must lie in this subspace, right? Which means first row exists at some point in the subspace. Does that make sense? Yeah. So so that's the row space, and any given x. Now, what happens? Back to the question of what happens if we take some x that does not exist in the row space of x, and you multiply it through and multiply it by a. What happens? And this is where the decomposition helps us find an answer. So a of x is going to be a of, I'm going to abuse notation and write it as xr plus xn, where this is the projection of x onto the row space, and this is the residue, right? And this, the direction in which the residue lives, is also called the null space of A, which means any point that lives in the null space of A will always get mapped to 0 in the output space, right? That's called the null space of A. So any point in the input space can be broken down into two components, a component that lives in the row space and a component that lives in the null space, right? And a of x, you can represent it as the row space component plus the null space component. And because a is a linear function, you can write this a of xr plus a of xn, right? And this is 0 because you're feeding this is a vector in the null space. You multiply it by a, it always goes to 0. Right? And so this is just a of xr. So the operation you want to think in your mind is, given any point in the input space which may or may not lie in the row space, when you multiply it with a, what happens is effectively you project that space onto the row space and transfer that, and find the corresponding output of that projection, right? So it essentially means this operation is effectively just pruning out anything that's outside the row space of from the input. Find the projection onto the row space and carry forward that point onto the output space. Right? So this concept of projection is super important. We're going to come across this concept, this projection again when we do linear regression, right? So what's technically, how do we calculate the projection? Right here, I just represent it as some abstract function called projection, and here I used the resulting vector after you do the projection. But how do you actually calculate the projection, right? And that's not too hard either. So projection. We'll start with the simplest case. Right? The simplest case where you have a vector. Let's call this V, some vector, and you have another vector. Let's call it B. Right? There are two different vectors. And now we want to project B onto the direction, onto the subspace spanned by V. Right? V is a vector and it induces a subspace, and that subspace is a one-dimensional subspace which is made up of all linear combinations of the vector B, which means take B multiplied by 2, you take V, 2V is part of that subspace, 0.5V is part of that subspace, minus V is part of that subspace. So this entire line is the subspace spanned by V, by the vector V. and now we want to project the vector B onto the subspace. Right? And how do we do that? For that, there is for a given V, there is something called the projection matrix. So the projection matrix of V is V transpose over V transpose V. We'll decipher this in a minute. Now, this is a projection matrix, which means you take this matrix and take any other vector. Right? It could be this vector, it could be this vector, right? And if you multiply B by this matrix, the resulting point is going to be the projection of B onto the subspace spanned by V. Now, why is that the case? That's the case because let's look at what's happening here. I'm going to rewrite this as, so V transpose B over V transpose V, and this is the same as V over norm of V over norm of V transpose B. Right? So V transpose V is the same as the square of the length of V. It's the norm square of V, and that so this is the square of the length. I distribute one of the length to this and one of the length to that. Right? So when you divide a vector by its length, you're effectively rescaling it into a unit length vector. Right? So now I'm going to call this say V tilde transpose B, where V tilde is a vector along V that has length equal to 1. Maybe this point over here is V tilde. Right? You can pick any vector along this on the subspace, and it's always going to result in the same projection matrix because you're rescaling it by the length. So it doesn't matter which specific vector you chose in the subspace, we rescale it by the length, come back to V tilde, and the projection matrix is V tilde transpose. Now, this, I'm going to write it as V tilde times V tilde transpose B. Right? And this we know is the, when you take the inner product between a unit length vector and any other vector, it's going to give you the length of the projection of this vector onto the unit length vector. Right? So if V transpose is V tilde is some unit length vector, you take any other vector B, the inner product between two vectors where one of them is unit length is going to be the magnitude of the other vector along the direction of the unit length vector, right? So this is going to be the length of the projection of B along the dimension of V, and then this is just some scalar. You're rescaling V tilde by some scalar again, right? So this is the projection matrix of some vector V, where the projection matrix projects the input that is fed into the projection matrix onto the subspace spanned by it. Is this clear? Any questions? Okay. Now, what happens if instead of one vector V, we have a collection of vectors, a bunch of column vectors? For example, we have, let's say, we have a subspace spanned by the a collection of 3 row vectors. Now, if these are the vectors onto which, whose subspace onto which we want to project x, we follow something very similar to this. In space, in place of v, instead of this being a vector, we will have a matrix where the matrix here will be some matrix x whose columns are vectors which make up the subspace onto which we want to project it. Right? In this case, it was a vector, it was a subspace with just one vector. But if we want to project B onto a subspace spanned by multiple vectors, right, then in place of V, we're going to use some matrix X whose columns are precisely those, a set of vectors which make up the subspace. Yes, question? They need to be linearly independent by definition, because those are, to make up a subspace, you need a set of linearly independent vectors, right? So take some set of linearly independent vectors from that subspace, right? And wherever there is V, just plug in X. So we're going to get X. This looks different from this, and that's because in V transpose V was a scalar, and you can divide something by a scalar, right? But X transpose X is going to be a matrix, and you cannot divide something by a matrix. Right? It's not even a meaningful operation. How do you even go about doing it, right? So the right way to think about this is to rewrite this as V. So I just rewrote this as V transpose V inverse V transpose, which is the same, and it is this form that can generalize into a matrix form, right? So the projection matrix for a set of columns is this, and we are going to come across this concept again when we do linear regression. So remember that. Yes.
Why you put the inverse in that particular order? So if that is for just a scalar, you could have put it anywhere.
I could have put it anywhere. Yeah.
Why import it?
So the question is, why did we put the X transpose X inverse in the middle rather than to the left or to the right? Right. So the answer is I don't know if this is a satisfactory answer, but this is the only thing that makes sense. If no other position will match the dimensions, right? So X is m by n. X transpose X or X transpose X inverse is n by n, and X transpose is n by m. So in a way, that's the only place where it kind of fits in order to kind of multiply things. I know that's not a satisfactory answer, but that's the only operation that kind of makes sense. Right. So this concept of what happens when you're this whole idea of projecting things and finding a point for which bijections exist and moving over is going to be a recurring theme. It's something you want to kind of understand really well, right? Any given for a given matrix A which is not full rank, there exists subspaces in its input and output space, and the dimension of the subspace is going to be equal to the rank of the matrix, and whenever you multiply a vector from the input space, what you're effectively doing is projecting that vector onto the row space, that's the input subspace for which a bijection exists, and then carry forward that point onto the output dimension. Which also means that now if we have a point that lives outside the subspace in the output space, and we want to find out what point in the input space will give me this as the output, which is effectively we're asking the question, what is A inverse? Right? That does not exist. For no point in the input space can we reach a point that lives outside the column space. Right? This point is unreachable. And when we cover linear regression, we're going to ask exactly this question. When we have a point that is not unreachable, what are we going to do about it? How are we going to find an input that, that's basically linear regression, which we'll cover on Friday. But this whole idea of subspaces, row space, null space, decomposition, bijection, these are things you want to kind of digest it well, and absorb them really well. Let's see. We have about 8 more minutes. All right, so we might be able to squeeze in this one. We might run over a little over time today, but I'll try to wrap up as much as possible and we can continue the rest. All right, so here we saw kind of a visual representation of what the matrix A does to the input and output. Now, next we're going to limit ourselves to only square matrices, which means the input and output spaces have the same dimensions. And for the purpose of visualization, we're going to only consider, let's say, a 3-dimensional space. Now, in this diagram, we had two different pictures for the input space and the output space. But now, because A is symmetric, A is a square matrix, we're going to overlay the input and output space onto the same space, right? So here, the input space and output space are being overlaid here. Now, let's ask the question. Now, let's ask the question. We saw what happened for choose some points, run it through A, you get an output point. Now, what happens if we take the unit sphere around the origin? By unit sphere, I mean just the points on the surface of the unit sphere. Think of it as a soccer ball that is centered on the origin. And you take every point on the surface, run it through A, you get a corresponding output point for every input point of the soccer ball. Right? How would the resulting shape look? Right? So that's going to look as an ellipsoid. It's almost like an ellipse. So that's going to be right. So what exactly happened here? It's a 3-dimensional input and output space. We started with the input as, we didn't have one input, but we had a collection of points as inputs, and that collection was precisely those points that live on the surface of a unit sphere. And let's say we we took this point in the input space, ran it through A, we got a corresponding out point, and that point is say this one. Right? So every point on the input surface maps to some point on the output surface of that shape. Right? We could have done this with any input shape, but sphere is easy to kind of analyze. Right? Now, similarly, you do it for another point. Let's say this point, and let's say that maps here. And let's say we pick, what color do we have? All right, green. Right? And let's say we pick this point, and that maps here. Right? Now, we saw what happens when we take some shape, for example, a sphere, and run it through A. Instead of thinking of running a point through A, now imagine running a full shape through A, which essentially means you're running every point in that shape through A and calculating the output point, which will be some other shape. So now think of A as taking as a shape as input and outputting a different shape as the output. Right? If the shape is some unit sphere around is the unit sphere around the origin, the output is going to be an ellipsoid. Right? Now, this ellipsoid, assuming A is also symmetric, right, will have essentially just two things. So first of all, so this was the input, this was the output, this one, which means there were two operations being done here. One is there is a change in magnitude, so the magnitude came down a little bit, and there's a change in direction. Right? A did essentially effectively two things: a change in direction and a change in magnitude. Now there are going to be some points along some points on the unit sphere for which the only change is going to be a change in magnitude and no change in direction. Right? And those are your eigenvectors. For a full rank 3 by 3 matrix, there are going to be 3 eigenvectors, right? And this is going to be one of them. And if it is symmetric, those eigenvectors are going to be perpendicular. Oh, sorry, I used the wrong color. I shouldn't have used. That's it. So this is going to be one eigenvector, and there's going to be another eigenvector which will map this point on the input to a point on the output, where the only thing that changes is the magnitude and not the direction. Yes, question?
I think it doesn't necessarily have to have 3 eigenvectors. It can only have 1 with its
I'm sorry?
But must it necessarily have 3 real eigenvectors? It can only have 1.
So does it necessarily have to have 3 eigenvectors? So it will have 3 eigenvectors. However, some of the eigenvalues may be 0. I'm going to come to that. Right? So this is going to be eigenvector number 1, for which the scaling is the maximum, right? And the eigenvalue is the ratio of the length of the input vector and the length of the output vector. So if the output vector is stretched a lot along the eigenvector, then you have a large eigenvalue, right? And if the eigenvector is shrinking the point closer to the origin, then the eigenvalue is less than 1. If it is bigger than the original point, it's greater than 1. Your point may also get reversed in direction, in which case your eigenvector is negative. Right? Now that's the eigenvector, and the eigenvalue is the ratio of the output to the input magnitude. It may so happen that when you take the unit sphere or a soccer ball as the input and feed it as the output may not be an ellipsoid, but it may be a flat ellipse, which means you lost a dimension. It got kind of smooshed into a 2-dimensional ellipse instead of having a rigid 3-dimensional ellipsoid shape. Now that means the eigenvalue along the third eigenvector was 0. Right? So along the third eigenvector, all the lengths kind of got mapped to 0. And does that make sense? Okay, sure. So now a question was asked earlier on. What's the meaning of the rank of a matrix? So the rank of a matrix is precisely equal to the number of non-zero eigenvalues. Right? If the matrix, so this is in a square matrix setting. If a matrix has full rank, then it means a unit sphere will always come out as some kind of an ellipsoid with the same number of dimensions. If you're rank deficit, the ellipsoid that comes out may have lost a few dimensions.